Welcome back to the deep dive. So have you ever wondered what happens when you smash together advanced physics and hyperscale computing? Well, you're about to find out. Today, we're doing a deep exploration of a proprietary system called the Forerunner Stack Architecture in Energy Systems. This is a system you really have to pay attention to. It's not just some, incremental upgrade to the grid. It's a total reimagining of energy management. We're talking about a custom-built ecosystem. It blends next-gen hardware, a pretty revolutionary storage idea, and some intensely sophisticated software control. Our mission today is simple. We're going straight to the sources you've sent us, cutting through the marking, and we're going to uncover what's really surprising here, especially how this thing manages energy flow in real time. Okay, let's unpack this.
That phrase, real time, is everything. It's the core claim of the entire architecture. And what makes it so different is how they say they do it. The Forerunner stack basically merges the physical world of power generation with this high-fidelity digital counterpart that's always running. This isn't just modeling. The whole system is designed to combine advanced physics with something they call digital twin simulation.
Okay, digital twin simulation. That term is key. For anyone not familiar, we're not talking about just a static computer model, are we?
Exactly. No, think of the digital twin as a kind of mirror universe for the actual physical energy system. Every temperature reading, every flow rate, every possible transaction on the grid, it all has an exact match in the software. And this virtual system is just constantly running millions of scenarios. It's predicting future states, finding bottlenecks, correcting for tiny little fluctuations, all before the physical system even has to react. It's an incredibly integrated approach. The physical and the digital are locked in this constant feedback loop to get, maximum efficiency and, just as important, maximum stability.
That holistic view really sets the stage. But before we get lost in the digital magic, we have to start where the energy is actually born. The source material confirms the heart of the system, the core reactor, is online. It's the engine that kicks this whole process off. So this core reactor, it's described as a next-generation electrolysis stack. And there's a performance number that just jumps out right away. It really sets the baseline for everything that follows. A 95% efficiency rating at scale. Now, 95% efficiency in energy generation is, well, it's monumental. But it also, frankly, raises an eyebrow.
Okay.
Historically, these kinds of claims, they tend to degrade once you move them out of the lab and into the real world.
That's a totally valid skepticism, and that's why a tech underneath it all matters so much. The source material is very specific here. It says they achieve this using proton exchange membrane technology, or PEM.
PEM, right.
Now, PEM electrolysis isn't brand new, but hitting 95% at an industrial scale. That suggests some real breakthroughs in the membrane materials themselves. The reason PEM is a differentiator is its power density and its ability to operate dynamically. It can handle fluctuations without degrading all the time. It allows for this really quick, clean separation of hydrogen and oxygen from water. It basically makes sure that almost every single joule of electricity you put in gets translated into usable, storable energy. If your input is already that close to perfect, it just reduces all the waste and complexity down the line. It's the physical anchor for the whole thing.
So the argument is that the material science in that PM stack is what makes the 95% benchmark robust, strong enough for real-world application. Okay, so that makes the input side clean, powerful. But if the core reactor is the engine, the storage component is where the system just completely departs from convention. We're pivoting now from generation to what they're calling the digital storage engine.
And this is where we stop talking about chemistry and start talking about, well, information theory. I mean, the traditional limits of energy storage are all physical, right? Volume, weight, decay over time. The system tries to just erase all three.
Here's where it gets really interesting and, honestly, a little bit mind-bending. The process is laid out very explicitly. Electrical energy is consumed by this custom high-density compute hardware.
Yeah.
And the output of that work isn't waste heat. It's high-value binary data.
A literal transformation.
Yeah, it's turning potential energy into pure information.
It's the ultimate dematerialization of a resource. And the obvious question is, what's the energy density of data? A lithium battery stores potential energy chemically. The Forerunner stack is storing the right to future energy digitally. The energy spent running the computers is converted into data packets that represent, let's say, contracts or quanta of energy value. And the revolutionary function here, which the source material confirms, is that this lets energy be stored online forever. And this is the big one, transported globally as information. The constraint is no longer pipes or high voltage lines, it's just the bandwidth of a secure fiber optic cable.
I mean, just think about the huge challenges with global energy transmission.
Yeah.
The infrastructure costs, the geopolitical choke points, the efficiency loss over distance. This just bypasses all of it. It potentially solves one of the biggest headaches in energy.
Hmm.
Physical constraints. You're not moving a heavy substance anymore. You're just moving data packets. But I have to bring the skepticism back for a second. When that compute hardware consumes the electricity to make the data, there has to be an energy penalty, right? Usually heat. Is that conversion process, electricity to computation to data, is it really more efficient than, say, just charging a massive battery?
That's the core engineering trade-off that defines the whole stack. The system is basically betting on the idea that the energy loss during that initial digitization is more than offset by the zero loss and instantaneous global transport you get afterward.
Ah,
Traditional storage loses energy when you charge it, when it's just sitting there, and when you discharge it, plus all the loss during transmission. The digital storage engine has a fixed upfront conversion loss, but once it's digitized, that energy as data can cross the planet with almost no power loss other than, running the fiber network itself. The real efficiency gain comes from getting rid of geographical friction.
that makes a lot of sense. So it's optimizing for distribution logistics, not just storage physics. And once that energy is converted, its success really depends entirely on the digital management system, the
Yeah.
software.
Exactly. Once your asset is energy as data, this highly valuable, movable thing, you need absolute millisecond level control over it.
Okay, let's move into that digital core. The first critical software component mentioned is real-time balancing. Its function is listed as providing a millisecond response to grid frequency fluctuations.
And this is where the rubber really meets the road for grid stability. Grid frequency is like the heartbeat of our whole electrical infrastructure. Tiny deviations from that standard frequency, even for just milliseconds, can cascade into blackouts. Especially now, as we add more intermittent sources like solar and wind.
Right, the renewables problem.
The Forerunner stack speed isn't just fast, it's basically instantaneous. A millisecond response time means that before a frequency dip can even register as a problem for older systems, the stack can inject or draw power to stabilize things. It just smooths out all the peaks and valleys. It makes the grid feel incredibly stable no matter how volatile the supply is.
So it's like a digital shock absorber for the entire grid.
Yeah.
And working hand in hand with that instant reaction is the second piece, predictive AI. This is where that digital twin really earns its keep. The predictive AI uses machine learning to forecast both energy load and weather conditions. So it ties the abstract digital asset back to the chaotic, unpredictable real world.
This is the proactive layer. The balancing is reactive, but the AI is looking days, weeks, even months ahead. It's pulling in huge data streams, historical usage, economic forecasts, weather data to predict exactly when and where energy will be needed most.
Okay.
And that forecast gets fed right into the digital twin simulation. The twin can pre-run optimization models, calculating the most efficient way to convert and move that energy as data across the network before the storm rolls in or the factories power up at 5 p.m. It creates this seamless, self-optimizing closed loop. It just guarantees you're getting the absolute highest value out of that 95% efficient reactor output.
That level of synchronization is really something else. It's far beyond simple automation. Now we have to look at how these optimized components talk to each other and how the whole network stays secure. The networking structure is based on mesh networking. This design allows for peer-to-peer energy trading between the individual nodes or stacks. It suggests a very decentralized, interconnected system. Units aren't all dependent on one central command.
The implications of that are massive,
Yeah.
especially for the traditional utility model. If individual cities or industrial parks or even college campuses can act as nodes and they can trade energy seamlessly with their nearest neighbor, it could fundamentally bypass the need for the huge regional utility monopolies we have now.
Hmm.
And that decentralization inherently makes it more resilient. If one node goes down, the peer-to-peer structure just reroutes the energy flow instantly. But, like we said before, if your asset is now pure, valuable information, security becomes everything.
Which leads us right to the final layer, cyber immunity. The source material says the system uses quantum-resistant encryption protocols. This isn't just about protecting the communication channel. This is about protecting the asset itself, the data that is the energy.
Precisely. When you're trading critical national infrastructure as data packets, you have to defend against threats that don't even exist yet. Standard encryption is vulnerable to future quantum computers. By using quantum-resistant protocols now, they are future-proofing the entire global energy transport mechanism. It's an acknowledgement that this data will be intercepted, it will be stored by adversaries, but it ensures that even with unimaginable future computing power, it will still be unreadable.
So if we step back, the system's strength really isn't in any one piece, it's the whole cycle. Ultra-efficient physical generation transformed into mobile digital information, secured by next-gen encryption, and all controlled by a predictive digital twin. It's a true end-to-end solution. And the source notes mention Access Our API, which tells you it's designed to be hooked into the world. All right, it's time to wrap this deep dive up. For you, the listener, let's distill the three big, surprising concepts from the Forerunner stack. First, that powerful foundation. The 95% efficient electrolysis stack, made possible by advanced PM technology that tackles the industrial scale problem head-on. Second, the truly revolutionary part, the digital storage engine, where electricity is deliberately consumed to create binary data, letting energy be stored and transported globally at the speed of light. And third, the critical control system, that combination of millisecond-level real-time balancing for stability, all overseen by a predictive AI using a digital twin simulation to create a proactive, self-optimizing loop.
If we connect this back to the bigger picture, the theme here is really about control and extracting value. This technology fundamentally shifts energy from a physical commodity that's constrained by weight and geography to a digital resource constrained only by bandwidth and security. It extracts the maximum value by just eliminating the friction of physical transport.
The Forerunner stack is defined by that perfect, closed-loop system of advanced physics and digital twin simulation. So what does this all mean for you? If a core strategic resource like energy can be stored online and moved around the globe as data packets, what does that fundamentally change about the geopolitics of resource scarcity, about national infrastructure, about the traditional power of nations that control oil and gas transit routes? That is a truly revolutionary concept worth thinking about.
Indeed, a shift in the physics can lead to a shift in power.
We'll catch you on the next deep dive.